In a previous video, we asked the question, what is software? In this one, we're going to ask the question, what is software engineering? To get us started, let's look at a few standard definitions first. Here's one from Pressman. It says that software engineering uses sound engineering principles. Okay, that makes sense. It's called software engineering, so it makes sense that you're going to apply engineering principles. And then it goes on to say that the product you develop should be economical to develop, reliable, meaning that the software does what it's supposed to do, and efficient, meaning it should run at a reasonable speed. Now, these are all very practical concerns that are hard to argue with. And you may want to add some other nice properties like usability or security, but the general gist of it is here. Here's the IEEE definition. The approach to software development should be systematic, disciplined, and quantifiable. The last one, quantifiable, is kind of interesting because it has to do with being able to measure the effectiveness of the software. We're also concerned with the development, operation, and maintenance of the software. So it's not just about development. Obviously, the software should operate correctly. That's part of reliability. But again, this last one, maintenance, is kind of interesting. We want to be sure we can maintain the software that we create. And that's part of what we need to do in software engineering. Remember that previously we said that software has to change for a variety of reasons. If I give you 5 seconds, can you remember the most common reason that software has to change? If I give you 5 seconds starting from now. And if you said that the most common reason is because of enhancements or adding of new features, you are right on. That is the most common reason. What are you doing when you're enhancing software or you're adding new features? Well, you're maintaining it. That's part of maintenance. So the point here is that maintenance is an important part of software engineering. In fact, Pressman gives a list of 4 very important properties of software engineering. The first, understanding the problem, may not seem like that big of a deal. But in fact, many software engineers think that this is the most important part of software engineering, understanding the problem. It's emphasized here because it's so easy to get this one wrong. This is all about gathering requirements and making sure you know what precisely you need to build. We're going to discuss this in detail in future lectures, but for now, just know that this is considered one of the most important parts and one of the hardest parts of software engineering. The second bullet point here relates to design. Good design is essential to software engineering. Remember that software development is at its core a conceptual activity, and the costs of development are in design rather than manufacturing, as they are in building something physical. This third bullet hits on Pressman's theme of quality. The point here is that anyone with a basic knowledge of programming can create a working program that might be good enough for their individual purposes. But if you really want to build something of quality, you have to engineer it. You have to have a disciplined process for gathering requirements. You have to have a good design that's flexible and adaptable to future changes, especially enhancements. And you have to have a strong testing strategy to ensure that your software does what you want it to do. All of these things are based on the fact that you want your software to be a high-quality product. Finally, we've already talked about the fact that our software has to change, and we have to build it in such a way that it's maintainable and adaptable to change. Let's look at software engineering from another perspective. Let's try to answer the question of how a programmer is different from a software engineer and how programming differs from software development. Before we see how one person answers these questions, take a moment to pause the video and think about how you would answer them. Okay, let's take a look at this distinction. Here's some observations on this distinction by Dr. Hadar Ziv of UC Irvine. First, a lone programmer writes a full program, which typically won't be very large, whereas a software engineer might just be developing one piece or one component of a much larger program. That component will have to be usable by other software engineers. In fact, it may even be used in other systems long after the software engineer who developed it has left the company. Remember that this is the case in product line software development, which depends heavily on a robust collection of reusable components. This second distinction is one of the most important. Software engineering is a team activity, and this cannot be emphasized enough. You can be an ace programmer and still be a bad software engineer if you don't have good communication skills and you can't work with other people effectively. Software engineering is a team activity. Finally, as we'll see in a few slides, programming is just one part of the software engineering lifecycle. We also have requirements gathering, analysis, design, testing, and so on. Programming is obviously an important part of the process, but it's only one part. Pressman wants to motivate the software engineering process by these developer concerns. The big ones, time and money, are up front here. Making sure that our software doesn't have a lot of bugs is certainly important. Understanding that the software will have to be maintained is critical. And finally, making sure that we know that we're making progress. This one may not sound so critical, but it's driven by the fact that a lot of software projects actually fail. And if you're going to invest significant time and money into a project, well, you don't want it to fail. So there should be some mechanism that allows you to determine whether you're on track or whether you're making progress towards your goals. Here's a picture that's directly out of Pressman. It emphasizes that the motivation of software engineering is founded on the notion of quality, of building a quality product. To do that, software engineers will employ some sort of process models. The details of the process may vary, but there are general framework activities that are common to all models. Once you've chosen a model, you'll adapt it to your needs, and you'll use various methods to do that. For example, you may decide here which language to use and which libraries or frameworks you will need. Finally, you'll choose the particular tools that you need to get the job done: IDEs, text editors, version control systems, compilers, and so forth. This slide is meant to give you a quick idea of what's involved in a process framework. Typically, you have a sequence of framework activities which can be accomplished relatively independently of one another. Within each activity, you have tasks to accomplish, work products to create, you have milestones, and you have quality assurance checkpoints to ensure that you're on track for building a high-quality product. In addition to these framework activities, you have umbrella activities. They're called umbrella activities because they have to be carried out during every single framework activity, so they cover or serve as an umbrella for all the activities in the process. Let's look at something more concrete. The 5 activities that you see here are those that Pressman tells us we will find to a greater or lesser extent in every single process model we encounter. Not only that, but the framework activities will almost always occur, at least roughly, in the order that you see them here, starting with communication, going through planning, modeling, construction, and ending with deployment. Also notice on the right here that you have some of the important sub-activities that comprise the main framework activity. For example, communication involves both product initialization and requirements gathering. We're going to spend an entire module talking about requirements gathering. Planning is made up of estimation and scheduling as well as tracking. Modeling has 2 main aspects, the analysis model and the design model. We're going to talk about both of these in detail in later lectures. Especially design. We're going to spend many modules talking about different aspects of design, like component design, interface design, and design patterns. Construction involves both coding and testing. Testing is something we'll also spend some time on. Finally, deployment involves delivery, support, and feedback. Recall that the umbrella activities are activities that are conducted throughout the entire development process. We need to continually track the project, manage risk, and ensure that we're always working in a way that will result in a quality product. We need to measure as much of what we do as possible to ensure that we're keeping on track. Now, there's one measurement in software development that has received more praise and criticism than all the other measurements combined. If I give you 5 seconds to think about it, can you say what this measurement is? Okay, the most ubiquitous measurement in software is lines of code, or source lines of code if you want to emphasize that comments aren't counted. This metric is criticized because it's easy to abuse, so that lines of code has very little to do with delivered functionality. On the flip side, almost every other metric that is considered good, like function points or cyclomatic complexity, has been shown to be highly correlated with lines of code. Interesting. Okay, technical reviews look at the work products you produce. Configuration management, another name for this would be change management. And if I give you 5 seconds, what do you call the type of tool that manages the changes you make in code? 5 seconds starting from now. Okay, a tool that manages the changes to code is called a version control system. Examples of these would be Subversion, Git, CVS, and we will be using Git for our first assignment. Reusability management determines which assets, code or otherwise, are potentially reusable in other projects, and it gives you guidelines for creating components with reusability in mind. Finally, work product management just refers to the coordination and management of the work products produced in the project. We'll finish with this slide. This is just a reminder of Pressman's philosophy on process models and adapting them to your needs. Remember, Pressman's book is about breadth rather than depth. He's not a proponent of any one process model or software engineering technique. Rather, he advocates understanding what's out there and adapting it to the needs of your particular project. In the next video, we're going to cover some general approaches to software engineering practice.